We present PANDORA, an approach to improve neural inverse rendering by exploiting polarization cues. In inverse rendering, the problem of uncovering 3D scene attributes from multiple images is inherently ill-posed. Each captured pixel is an intricate function of unknown 3D geometry, material properties, and environment lighting. Existing neural radiance field-based approaches excel in realistically rendering the final image, but often fail to perform inverse rendering under challenging scenarios. Such as here, Neural Pill renders the combined image well, but fails on decomposing the image into its underlying scene attributes. A key insight is that polarization is useful and practical cue for improving inverse rendering. Polarization strongly depends on material properties and surface normals. Here are the physically based renderings of a diffuse specular components of a glossy sphere in uncontrolled lighting. The degree of polarization is higher for specular and depends on the elevation angle of the normals, while the angle of polarization is orthogonal for diffuse and specular components and depends on the azimuth angle of the normal. With the advent of commodity on-chip polarization sensors, capturing polarization has become practical. These cameras have a grid of polarizer and color filter arrays, enabling RGB polarization capture in a single shot. We utilize this snapshot polarization camera to obtain multi-view polarization images. Recent progress in representing the scene properties as coordinate-based neural networks has facilitated neural inverse rendering, resulting in impressive geometry reconstruction and novel use synthesis. In particular, we borrow ideas from two recent works in the space: modeling geometry using sign distance functions as demonstrated by VolSDF, and modeling reflections using integrational direction embeddings as demonstrated by RefNav. We propose PANDORA, a polarimetric inverse rendering approach based on implicit representations. From multi-view polarization images of an object, PANDORA jointly extracts the object's geometry, separates the outgoing radiance into diffuse and specular, and estimates the illumination incident on the object. The pipeline of PANDORA is as follows. On sampling a position x on the view ray, SDFnet estimates the sign distance field and geometry features. Derivatives of SDF provide us the surface normal. DiffNet, RoughNet, and MassNet output the diffuse radiance, the roughness, and the 3D occupancy value at the position x. IlluminNet exploits the integrated directional embeddings and estimates the specular radiance. By dialing down roughness later, we can also estimate the incident illumination. Given the diffuse specular radiance and surface normals, differentiable polarimetric rendering outputs the rendered Stokes vector that we compare with the captured Stokes vector. The loss between the rendered and captured Stokes vector is then used to train all these networks simultaneously. PANDORA outputs clean surface reconstructions free from texture artifacts, renders sharp diffuse texture, and models strong specularities accurately. PANDORA also estimates incident illumination under practical unstructured scenarios. The diffuse and specular radiance fields, we can generate renderings of the object under novel appearances, such as editing diffuse color or changing the object appearance from glossy to metallic. Thanks for listening. Please do visit our website for code, dataset, and more details.